Hello everyone. Today we're going to step away from raw algebraic calculations and look at calculus through a visual lens. We are exploring the geometric relationship between two linear equations, x equals 2y squared plus 5 and x equals 7 minus y squared. Our goal isn't just to solve for an answer, but to intuitively map out the physical region these lines trap between the horizontal thresholds of y equals -1 and y equals 1. By focusing on how these boundaries behave spatially, we can clearly see why integrating along the y-axis is the most elegant way to calculate this bounded area. Let's build our graph. First, let's plot our first boundary line. X equals 2y squared plus 5. Because this equation expresses x in terms of y, it's highly intuitive to think about it vertically. If we look right at the center where y equals 0, our x value is exactly 5. That's our anchor point on the horizontal axis. Notice the relationship as we move. For every single unit we climb up the y-axis, the line shifts 2 units to the right along the x-axis. It gives us a steady, positive slant that stretches across our system, establishing the left-hand boundary of our upcoming region. Now, let's introduce our second curve, x equals 7 minus y squared, shown here in blue. Spatially, this line behaves quite differently. When y is 0, x starts further out at 7. But because of that negative y relationship, as we climb higher up the grid, the line pulls backward to the left. As these two paths cross, they collide at a very specific point of intersection. Geometrically, they trap a wedge-shaped space to the left of their crossing point, giving us a clear structural framework for how these functions interact. Because our region is tightly bound from y equals -1 to y equals 1, let's highlight the exact space we are measuring. Look at how clean this geometry is. If we slice this area horizontally from the bottom floor to the top ceiling, our right boundary is always governed entirely by the blue curve, and our left boundary is always governed by the orange curve. The spatial relationship doesn't break or flip anywhere in the interval, demonstrating visually why integrating with respect to y is the most direct mathematical approach. Now that we have visualized our bounded region, let's translate this geometry into its formal calculus setup. To find the area bounded along the y-axis, our formula subtracts the left-bounding curve from the right-bounding curve, integrated between our lower and upper horizontal limits, c and d. Looking at our graph, the rightmost boundary is our blue curve, 7 minus y squared, and the leftmost boundary is our orange curve, 2y squared plus 5. Our interval is bounded from a floor of y equals -1 to a ceiling of y equals 1. Plugging our functions into the setup gives us the definite integral from -1 to 1 of the quantity 7 minus y squared minus 2y squared plus 5 with respect to y. By grouping our like terms together and simplifying the algebraic expression, our integrand condenses beautifully into the definite integral of 2 minus 3y squared dy. This represents the exact mathematical core of our trapped area, ready for direct integration. Integrating our terms with respect to y yields the expression 2y minus y cubed, which we evaluate from our lower limit of -1 to our upper limit of 1. Applying the fundamental theorem of calculus by evaluating at these boundaries leaves us with a final, mathematically precise area of exactly 2 square units. This cleanly finishes our quantitative analysis, matching our geometric visualization perfectly. By translating these quadratic equations into a physical workspace, we gain a clear spatial understanding of our problem. The perfect symmetry of these two sideways parabolas traps a precise balanced region. Transitioning this visual layout into a definite integral along the y-axis allowed us to bypass complex piecewise calculations, yielding our final calculated area of exactly 2 square units. Seeing these boundaries locked together on the graph proves that calculus isn't just about abstract formulas on a page. It's a powerful tool for mapping and measuring the spaces around us. Thank you so much for watching, and I hope this provided an intuitive look at integrating along the y-axis.